Hello and welcome to another presentation, this time on binomial expansions, just at AS level. I'm just going to be going over the material that you need at AS here. Now, I always think the wise thing to do is start with Pascal's triangle when doing binomial expansions, because the students can see straight away the connection with it. Pascal's triangle as well is a lovely thing to teach students for a mathematician because there are so many patterns in there. Picking one just off the top of my head, you can see that the very first row, 11 to the power of 0 is 1, 11 to the power of 1 is 11, 11 squared is 121, 11 cubed is 1331, 11 to the power of 4 is 14641. Sorry, I've smudged the work. Sadly, the pattern breaks down on the on this row here. As soon as you get double digits, it doesn't work anymore. But that's a lovely little pattern just to start them off. You've also got the ones down here, then the natural numbers, and the triangle numbers down that row, tetrahedral numbers. You've got the fact that every row seems to add up to a power of 2. You've got the fact that if the second number is prime in that row, then all the other numbers will divide by that number. The patterns are endless in Pascal's triangle. They really are. I've only really scratched the surface there. So it's a lovely thing to teach. You can straight away get students interested, or you can approach it anyway from a variety of different angles. But we're obviously doing expansions. Now I like to point out straight away that x plus y to the power of 1 expanded is obviously x plus y. But if we expand x plus y squared, we get x squared plus 2xy plus y squared. Same thing for x plus y cubed, and you'll see that we're using the next row of Pascal's coefficients. So we get x cubed, the power goes down on x and up on y, x cubed plus 3x squared y plus 3xy squared plus y cubed, and so on and so forth. So Pascal's triangle is dead handy if you're multiplying out high powers on a bracket. It's useful for stuff like this, and this isn't an unusual question. Expand 3 minus 2x to the power of 4. Now naturally we're going to need the next row down. We're going to be doing 3 to the power of 4 first. Then we're going to be adding 4 times 3 cubed times by minus 2x. Then 6 times 3 squared times by minus 2x squared. And then 4 times by 3 times by minus 2x cubed. As you can see, one power goes down, the other power goes up. And then minus 2x to the power of 4. That gives us, after we've tidied up, an answer of 81. Now the powers should alternate. Minus, what have we got there? 27 times by 8, so that's going to be minus 216x. Then we've got 9 times 4 times 6. I think that's also, if I'm not mistaken, 216x squared. 9 times 6, yeah, cool. And then the next one we're going to have 8 times by 12, which is going to be minus 96x cubed. And lastly we're going to have plus 16x to the power of 4. And that's a fairly common kind of question for just a very simple question at AS. They can make it a little bit tougher though, and when they make it a little bit tougher, it tends to be because n choose r is involved. So let's look at what n choose r is all about. Is often notated like this, and we would pronounce that n choose r because of what it means in probability really, and in permutations and combinations. It's sometimes written as a vector, n r like that. You can use either type, but the formula for it is the following: n factorial over r factorial n minus r factorial. Looks quite intimidating because of the exclamation marks, the factorial sign in it, but remember factorial simply means, well, for example 6 factorial would just mean 6 times 5 times 4 times 3 times 2 times 1. And yeah, it's called n choose r because it's a number of ways of selecting r objects from n. That's what it is actually, that's the reason why it's called n choose r. But what does it really mean in terms of us for Pascal's triangle? Well, let's take this element here. That is actually going to be worked out by doing 6 choose 2. The reason is n is how many rows you have to go down, but you always start from 0. So that's 0, 1, 2, 3, 4, 5. And as you'll see, we're 6 rows down, because that's the 6th row down here. That's going to be our value of n. And then r is the number of times we've gone across that row. Well, bear in mind, you always start at 0 once again. This is for r equals 0. I'm sorry about that, it's not really coming out so well. R equals 0 is the 1, R equals 1 is the 6, R equals 2 is the 15. So 6 choose 2 represents, if you like, actually 7 rows down and 3 rows across, because you always start from 0. So let's see if the formula really works. Well, 6 choose 2 means 6 factorial over 2 factorial, and then 6 minus 2, which would be 4 factorial. Now, calculators will work this out for students nowadays, but they really, it's not very difficult to simplify it yourself. This is 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 4 times 3 times 2 times 1. Now, normally I wouldn't write down this intermediate step because that's always going to cancel with that. In other words, you're always going to get rid of the highest factorial on the bottom by just writing the top without a factorial on it. And then we've got 6 times 5 over 2 times 1, which is 15, just as we said it would be. So that codes Pascal's triangle for you. But please remember, you always start with n equals 0 and r equals 0, n being the number of rows down, r being the number of elements across in that row. Now, why does this get pretty tricky? Well, it's for simplifying n choose r expressions when you haven't got two numbers. Let me give you an example. We could simplify, for example, n choose 2. n choose 2 is simply m factorial over 2 factorial n minus 2 factorial. But because of the way the factorials work, we're going to get n times m minus 1 times m minus 2, and I'm just going to put dot 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 there. But on the bottom we're going to have 2 times 1, but then we're going to have m minus 2 times m minus 3 dot dot dot, and they're going to cancel, leaving just n m minus 1 over 2. Now that makes a lot of sense to me because that formula looks very, very familiar. It looks just like the formula for triangle numbers, and sure enough, all the elements which are of the form n choose 2 are on that leading diagonal. And as I said earlier, the first diagonal gives you the 1s, the second diagonal gives you the natural numbers, just 1, 2, 3, 4, 5 going up. The third diagonal gives you the triangle numbers, and sure enough, we've proved that with n choose 2 we get the triangle numbers. Now, handling confidently expressions involving n choose a constant is imperative if you want to be able to prove properties about Pascal's triangle. It's particularly useful actually in the hockey stick puzzle I've given you to prove, so bear that in mind. Now, in terms of how they can make this difficult in AS level, what they might do is talk about the coefficient of x squared being twice the coefficient of x cubed, and what you might need to do is work with n choose r in this kind of manner, simplifying it and then rearranging the equation. Anyway, I hope that's been a nice little reminder for you of how these things work, n choose r and Pascal's triangle and binomial expansions. If you want to see an expansion used as approximation, watch the next video on binomial expansions at A2. Thank you for listening.